just quickly, the unsupervised learning, right? It's sort of like two things that we tend to do quite a bit. One called clustering. The other one is dimensionality reduction. Right? Now, remind me, because you know, I only see you once a week. In terms of cluster analysis, we only cover things like KB, correct? All right? Yeah. And dimensionality reduction, I mentioned DCA, correct? Yes? Yes or no? Whatever it is, they understand it. Okay, that's what you know. Okay? Now, this, okay, these two, and what are the different kind of analysis? Again, this special technique. By the way, another one that we use called yeah, I like to talk a little bit about that today. So what I like to do is, yeah, let me write that one. Neural network, and the other one is sort of like 3D based. Okay, now neural network. We haven't got all of this. We haven't covered all of this, but 3, 4, radius 3. Okay. And reinforcement. So that's just to confirm what you are. So this one I think you haven't covered, right? So you are responsible for KB. This is the KB. I think I'm telling you what you're responsible for in that, but should be responsible for everything. But I understand that I'm used to. In real life, by the way, nobody ever done this before. Even if it was a job that you reevaluate on KPI and ABC, in the end, you get promoted on the whole package. Right? You can't say, oh, I feel this thing really well, 1, 2, 3, why don't I get promoted? Yeah, it's always a whole package. It's always a whole package. But, this will stop you maybe harassing my TA about what's going to be on. So this thing, I guess, there, like that. So maybe one of these something that you have to know really well. Yeah? Because they give you a different flavor. So you can think of all this as a special. So today, by the way, I'm going to talk a little bit about, I think, I'd like to talk a little bit about this. Now this thing, as I understand, we haven't really talked about, right? This is 63. Yeah? So the party on this thing. And then, like I said, go back to linear algebra. Talk about system of equations, blah, blah, blah. But we haven't talked about determinants and eigenvalues. That's something that's important. Well, yeah, you have to think about what system of equations. Right? And we have calculus, right? Calculus. Differential calculus. There's no, I don't want to say there's no, yeah, you're not really responsible for integral calculus all that much because it's not immediately relevant. Okay? So, but I don't want you to get integral calculus. So, differential calculus and how they find the way to set. From state so what are we going to talk about? Okay, so that's the topic. This is part of today. Okay, so we're talking about it. Yeah. First. Decision 3. Now, I will show you something from very classic way of looking at things. So let me share. Do I have to share? Okay, I have to share as well, right? So I have to share my this one. Oops, sorry. Not this. Iris data. Okay, Iris data. It's very famous. Iris flower data set. Okay, have I mentioned this to you? Probably not. Okay. Anyway, let's look at this. You know what an iris is? You know what a flower is? Okay. Wikipedia simple. Okay. Oh, I have to share one at a time. I'm sorry. Yeah, you should show. Anyway, I'm just gonna draw. Okay. You guys know what a flower looks like? Okay. Well, what happens is when it's a bud, think of a rose. When it's a bud, right? It has this green thing that covers. Yeah, it has this thing that covers. This thing is called sepal. Yeah. When it gets bigger, this thing opens up. Then you get more flowers. The flowers have petals. Yeah. That's how sepal do things, right? Now, the iris, after an iris, has a threefold symmetry, but unlike the rose, the petal, yeah, doesn't overshadow the sepal. So in other words, you get something like this. In normal rose, in normal flower, the sepal just sort of like covers the bud, and once it's open, it's developed. So the iris is kind of predominant. Yeah. So you get this kind of threefold symmetry. Yeah. Now, if you take this measurement, this is the length, this is the width, this is the length, this is the width. We have 4 measurements for each flower. 4 measurements each flower. Yeah. Based on this, you have 3 kinds of flowers. 3 kinds of iris. Okay, 3 varieties. Yeah, so it's not just big, medium, small, but it's different proportionalities. Okay, so if I give you the measurement, can you guess what variety it is? Can you identify it? Yeah, in scientific term, it is called identification because you already made 3 paths, right? The identification, but in machine learning, is called classification problem. So we're supposed to have petal width and length petal and width of sepal. Oh, it's coming out. It takes a long time. Length of sepal, this thing. Yeah? And you're trying to create some function that is a classification K. Where K belongs to color with quantification. So what kind of problem it is? It is classification, right? Is it binary classification? No, it's multiple classes, 3 classes, right? But you can also think of it as 3 separate binary classes. In other words, is it 1 or not? Is it 2 or not? Is it 3 or not? So you can always do that. Every time you have if you have m class, you can always separate it to m different binary classifications. Okay? Now, normally that doesn't really work because what if it gives you 2 classes, right? It says yes for class A and class B. How are you going to decide? So you don't want to do that. You want to put them all together. But you can think of them as multiple binary class. Okay? Now this is it. This is. Can I get rid of that thing? I can't. Now, this is what I mean by visualization, right? The visualization, just do a scatter plot of 2 variables at a time, 2 at a time, because it is 4-dimensional, right? I can do this pair, this pair, this pair, this pair, this pair, this pair. This is all the pairs, right? And because I know ahead of time what time it is. By the way, I'm just going to call it gray, blue, or green variety, right? It's actually all the same color. Gray class, blue class, green class. You can see that it's separated nicely, right? Separated nicely. Now, this is not a clustering exercise, right? If it's a clustering exercise, you get no color. And then you say, this lamp, I keep one color, this lamp, I keep another color, this lamp, I keep another color. That's unsupervised learning. That's clustering out. In this case, no. In this case, you knew what class it is. So it is supervised. It's red, blue, green. But notice how nice it is. It's very nice, right? It actually separates nicely. If you think about it, you can almost do a circle around green, circle around blue, circle around red, based on this value, right? Based on this value. Yeah. So let's imagine. Yeah, let's imagine. I'm just going to take one dimension. Yeah, just take one. In this case, I can almost say this is red. Just say one color, red and green, blue. It's almost like, in this case, for example, I can make this line. Whatever that value is, if it's greater than this, it is a blue. And I'm sorry, I don't have to do anything more. Okay? The feature is intricate, right? But that's what you need to do. Okay? So you separate by here. Okay? If y, whatever y is, y may be what it is. If y is greater than, let's go that right. This is theta. If y equals to theta, greater than theta, it is a d. Yeah. Otherwise, I go on and I say if x is less than gamma, x greater than gamma 3. Otherwise, it is greater. is a nice classification scheme, right? Right? Whatever that is, this happens to be very nicely separated. I take the value, some kind of measurement. If it's greater than this, I'm done. I know it's a blue, right? Because the blue is really whatever one dimension different from the other. The other two, I have to go to separate on the different axes. Okay. Now, this kind of thing looks like a decision-making thing, but it's not decision of what to do, but it's decision on the judgment, right? If I look at you and your y is greater than theta, I think you are blue. So I decide. So it's not to decide what to do, but it's decide on classification. Now this is done different because I get this blue, nothing else. But in this case, I'm still left with red and green, right? So I make another branching, and let's say, what is your x value? If the x value is greater than gamma, I will say you are green. Otherwise, you are red. So now I end up with a pure node, right? So once you're here, you are green, red, blue. My classification is done. This is based on the data set. Again. So now the model has learned. How does it learn? It learns by identifying theta and gamma as well as this structure. Okay. Now, if you think about it, there are 4 variables here, right? So it could do 4, you can do many layers, right? But in this case, it's so simple, just 2 is enough, x and y, whatever that is. It could be sepal length, sepal width, or whatever. Okay. Yeah, you're done. You're done. You're done. Well, this, if you put it upside down, it looks like a tree. Okay? And here, the decision point. So this is called a decision tree classified. This is called a decision tree classified. Yeah. Now, this decision tree classifier is very nice. It's very simple. Because the data is very nice, it's very simple. Right? Now, I'm going to make just the 2 variables useful, but I'm going to make it more complicated. That's it. Right? Now I can't make a straight cut anymore. But you know what? I can. I can make a straight cut and say like this. Let's say this is my green. Right? But this is not done. I'm not done yet. Keep going. Go back to y again. Use y1. Use y again. This is my data 1. So I'm going to make data 2. If y is greater than theta 2, okay, I will call it green. Otherwise, I call it red. That. So even though the data are not separated orthogonally like this, you should be nice. You can still keep going. It's like saying that you're trying to create a non-linear partition, like a neural network, but you can only do linear partitions at a time. So the analysis is perfect actually. Remember the neural network? The neural network is a whole bunch of neurons, and each neuron separate left from right or top from bottom at whatever angle. If you have 2 neurons, then you can start creating some kind of non-linear separation. This is a little bit like that. Every junction only separate left from right, top from bottom. But by using combinations sequentially, you actually create this kind of non-orthogonal separation. That's what you want to do. Okay? Now, this happens to use only two variables, but for the iris class, instead of having just 2 dimensions, you have 4 dimensions to play with. Okay? 4 dimensions to play with. And that's what the decision tree algorithm does. Okay? Decision tree algorithm does. It's solving this problem by looking at one dimension first, make a left-right comparison. If it's pure class over here, you do that. You do not keep going. Okay. Now, something else as well. What if I say, I don't want to keep going, I want to stop? This is important. This is important because in real life, this is what you do. You don't want to keep going. In this case, you can keep going a few times, but you imagine in real life, you have 100 variables, you go pretty deep, the tree can go like forever. Okay? So you have to stop at some point. So if you stop here, it's like you can't draw this anymore. You have to stop here. Okay? You have to stop here. Then what do you do? It's neither green nor red, right? It's neither green nor red, but it has more red than green. It has more red than green. So you would say it is red with probability. And this is 80%, this is 20%, 1 okay. So the decision tree doesn't end with a pure classification, but it ends with a mixed classification. Then it gives the classification to the result. Okay. So you can only make 2 cuts. You can only go two levels. This is called depth. 1, 2. This is depth. My depth, my maximum depth is 2. Now this one happens to go to 1 and be happy. I will give you that. But what if I can't go more than 3? So my max depth is 2. 1, 2, 1, 2. And once I get to 2, this one I'm very happy. I get perfect classification, all 3. And this one I get red and a little bit of green. So I can't say that this is definitely a red. I say it's a red with probability 1/8. That's what a decision tree classifier does. So most of the time, it's not going to give you 100%. It's going to give you probability of 1. Right? Is this simple enough? This is simple as it gets. Okay? So this decision tree is very simple. Let's look at how the decision tree on the iris data look like, right? Let's see. Decision tree solution iris data. There's going to be a picture. I mean, this is been done 1,000 times in life. Okay, I want you to look at 2 pictures. Okay, look at this one first. This is actually what the decision tree look like. Okay. Now, I can't read. Hold on. I think sepal width. Okay. I think X3. The first one say X3. I think X3 is this. I don't know. Yeah. Details different. It's saying there are 4 of them, right? If X3 is less than 0.8, it is class red. It's class red. Because class red is unique, you know, it's just separated by 1 dimension. If it's not, you go to X3 again and you separate by 1.75. I think this is like a petal length or something like that. And then you separate into this and that. Now, if I stop here, if my max depth is here, I would say this is green with what probability? Can you guys see? Let me make it bigger. It is green with probability 49 divided by 54. Can you see that? Right? Because because it has 49 green and 5 blue. That it's not pure. It's not pure class yet. It's 49 green, 5 blue. So what the probability of green is very high. 49 divided by 49 plus 5. Now over here, what about this? This is still not pure. It's blue. But how many blue does it have? 45 blues and 1 green. So the probability is 45 divided by 46. So it's a very high probability. And then you make the final cut and it gets a perfect. Okay? So this is it. This is solved. This problem is solved for this data set. So literally, it's learning from data by chopping up the data. In this case, the class has 50 blue, 50 red, 50 green. So it has 150 data points. Okay? And it's running this thing down. Okay? So when you get to the final, it's always perfect. But this one has 49 green, nothing else. This one has 1 blue, nothing else. This one has 3 blue, nothing else. This one has 2 green, nothing else. So when you get to the bottom or the terminal node, it's called a leaf. Remember, this is like a tree, so the end is like a leaf, the leaf node. Okay? When you get to a leaf node, you get perfect separation. But if you stop before that, you still get a mix. Yeah, possibly a mix. So that's what it looks like. And this is what it did in the original space. Okay? It's making this kind of chopping. See that? Chopping and chopping. I think the red one is easy to take one chop, but the blue and the yellow here take a few chop. But it's always vertical chop. Okay? And horizontal chop. Okay? But again, the problem is not vertically segregated or horizontally segregated, so you have to do it 2 times. Just like in the case with the neural network, you use this kind of left-right, the one neuron, the other neuron goes left, up, down. You have a combination, so you get all kind of very interesting pattern. Right? So this is how decision tree classifier works. Now, what happens when you get a new flower? Well, you just pass it through. You pass it through here. Okay, pass it through here. Right? If it's x3 is less than 0.8, you're done. Okay, you rate. If not, you go here, 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 here. Okay. If your algorithm stops here, say max depth is equal to 3. 1, 2, 3, and you end up here. Then you would say you have a 4 divided by 6 probability of being blue. 0 probability of being red because red is gone. Okay. Now this, why do I give you this kind of detailed look at decision tree? Because in real life, in my life, in my professional life, decision tree is usually the preferred tool for a lot of projects. In other words, when I run the project, you classification. I have the PA here, run a whole bunch of experiments, some with neural network, maybe support vector machine, maybe decision tree, like for tree. And I will take the winner. Yeah, the one that has the best performance. But if the performance are similar, in terms of accuracy, in terms of efficiency, true positive, true negative, false positive, false negative, all the performance are similar, the client, my consultancy client, will always prefer decision tree model. Because the decision tree model explains how it makes that choice. Imagine, this is not 3 kinds of flower, but 2 kinds of borrower. Good borrower, bad borrower. Okay? And I developed 2 models. One is a neural network that gives you a good prediction of whether or not this person is going to be bad debt, whether or not this person is going to be good debt. right? So predict default, basically. Okay, one for bad, one for default. And the other one is not, so say I built this one based on neural network model. Okay? It's not a black box, but it looks like a black box with mine. I make another thing called decision tree, and it gives similar accuracy. Maybe not as good, but acceptably close. My client will always choose decision tree because I can create this thing. By the way, what's this? This is my visualization, right? Because the algorithm only gives you the probability of great, good, weak, probability of good debt or bad debt, right? But I can visualize details of how the model works. So the client who says, oh, I can see why the bad debt is separated by the asset value or the income level or education. I can actually interrogate the factor one by one. Who really matters? Not only that, let's say I get these two boxes. This is high probability of default. This is high probability default. This is low probability default. This is low probability of default. I can actually look at the number that goes through. So if I'm going to target the group of clients, I'm going to get low probability of default, but with the biggest flow, right? Because this is good, low probability default. This is low probability default, but this is only 2 people, whereas this is 5,000 people. So certainly in terms of marketing strategy, not only do I say what kind of people I should go after, I can say, well, there are 2 kinds of people I should go after. One looks like this. One has this characteristic. The other one has that characteristic. But this characteristic is a very niche market, small, only 2 people. Whereas this is a huge market, 5,000 people. Obviously, I'm going to target the 5,000, right? My campaign cost, my efficiency of the sales force will be much. So you can do all kinds of stuff. So it's not just seeing the likelihood of good debt, bad debt. It's saying how good, why good debt, why bad debt. If good debt, how many groups of people are considered good debt, and which is the big chunk, which is the small chunk. Now I can use the other way as well. Instead of focusing on the big chunk, I can say, oh, big chunk, everybody knows that. Everybody's already lending to these people. But the small chunk, hey, I can explore it. Maybe these people are good, but they have not been, the reason they don't populate the data set is because most banks deny them. But they're actually good. So we can find niche market, right? So in this case, I don't want the big flow, I want a small flow with equally good rating. I can do all kinds of stuff. So decision tree is extremely useful in that sense. Right? It's not always the case. This is a little bit like statistic versus machine learning. Statistic is not as powerful as apply to all cases, but if it does, it gives you more information. Decision tree versus neural network is a little bit like that. There's a lot of problems that decision tree would just give up. Okay? Neural network will be okay. Neural network can handle it. Decision tree can't handle this. Just give up. But if it doesn't give up, in other words, if it does perform just as good as neural network, it gives more information. It gives more things to play with, right? So this is where you have the preference. You always have preference for things that are more transparent. Okay? There are preference for things that are more transparent, that has less number of parameters. So this is one of those. This is one of those. So you prefer simple things, not because they're simpler. You say that if the performance are on the same level, would you prefer a neural network that has 5,000 parameters or something like this? Right? Maybe the neural network doesn't have 5,000 parameters, it has the same number of parameters. Still, this is easier to explain. This is easier to visualize. Not only is it easier to visualize, I can use it for other purpose. Like I said, identify the good debt that is currently a small number of the population. Oh, I don't see a lot of these people, maybe because we haven't really given them approval in the past, but they are actually good. Let's explore. Let's make them big. So it's small because in the past we screened them out. Not because they're bad. They're good. They're good. We just didn't have a lot of them. So this is my opportunity. This is my hope, right? You know, everybody's looking at the big chunk. I'm going to look at the small chunk and make it my niche market. Yes, yes. Because the way the decision tree does, it only looks at one variable at a time. Yeah, you have to kind of like do sequential cut. Cut one, cut two. No, it still can do that. It still can handle that. It's not very elegant. No, it's not. It's not like a neural network that you can get a smooth. No, but you can certainly separate. You know, even if something like this, you can do separate, and then separate, and then separate, separate. Okay. The point is, in order to get all this, you need a lot of, not a lot of branching, branching, lot of them. So if it happens to be like this, yeah, you're done. If it's something like this, oh, you have to do something like cut once, cut again, cut again, cut again. Doable. Yeah, in fact, you are almost guaranteed, okay, to get to a single data point. You can separate. With the decision tree, you go down deep enough, you can isolate a single point. Just like a neural network, yeah, but it's not elegant, it's messy. Classification, yeah. Oh, no, everything we do is for the new data. Like I said, analysis here, you don't care about the 150 flowers. Yeah, exactly. This is all learning. This is all learning path. Yeah? The next flower that you care about. Yeah? Now, when I said to you that the max depth is usually set because we can't keep going down forever. Well, actually, the machine doesn't care. It will go down forever. The point is that if it goes down forever, you are moving the data. So in fact, you don't want to go that deep, even if the computer can. In fact, in a normal code of decision tree, there's a parameter called max depth. And you set it to unlimited, it will go down all the way. It will go down all the way. It will go down to a single data point if you can. Okay? Because the machine doesn't get tired. The point is that if you use that tree, you're going to be like micro segmenting, which is not true. This is just some noise. So you want to say max depth is equal to 5. So go down 5 branches at most. Okay. In this case, you know, a fair question would be, what's the max depth of this problem? It has to be, well, it certainly can be higher than this, higher than what you see, but certainly it can't be smaller than. Well, this one doesn't have, this one because it has pure classification. I probably guessed that when I ran this, it was, when whoever ran this, put it as unlimited. But let's say you get something like this. You get something like this, okay? Just up to here. And you don't get perfect classification yet, but you stop. What's the max depth you can guess? 1, 2, 3, right? Right? You can look at the result and infer backward, okay? Now, in this case, if the max depth was 10 or unlimited, it gives you the same result because it only goes down how many times? 1, 2, 3, 4, 5, okay? So max depth of 5 or max depth of 6, max depth of 7, unlimited max depth will give you the same thing. Because it only takes 5 branches to get perfect separation. Okay, pure separation, pure node, pure leaf. But yeah, if you're like, you don't want to get properly. So this is really what I want to cover, decision tree. Now, the thing is, decision tree are considered weak learner compared to neural network. Weak learner means it's not powerful. Okay? So, how do you make it more powerful? Then there are 2 ways of making things powerful. One called backing, one called boosting. Okay? Backing means, let's say you are a decision tree. You're okay, you're not that great. maybe you are a different decision tree using different data sets. Okay, maybe I try, instead of giving you all 150 flowers, I give you 50 flowers, give you another 50 flowers, I don't know. Okay, this sort of like 5 different things. You end up with a different tree and then some kind of voting. So you would say it's a red. If you say it's a red, oh great, you agree. Let's make it red. Okay? If you say it's blue, you say it's red, but maybe you have higher confidence, probability 0.9, maybe some kind of voting. So this is like a bag, putting different models in a bag. And that's what a random forest is. Yeah? It's giving different trees, different data set, some kind of subset of the whole 150. So you don't end up with the same tree. If you give everybody the same 150, you get up with the same tree, right? So it's kind of like randomly. Maybe I think this is 50, I think that's 50, I think it's 50. How many can of you? So it's forest. So that's what random forest is. It's a backing of decision tree. Boosting is a little bit different. It's saying that I train a tree. The tree is going to have some error. I'm going to say those samples that has error, I'm going to pay a lot of attention to it. So oversample the error and then train a second tree. And that's still going to have some error. So whatever is the error case, I focus on that. I train the third tree. So it's kind of boosting the power with respect to the error. So that's called gradient boosted tree. Yeah, it comes from boosting decision tree. But it's all based on tree. So it's kind of tree-based. Okay? It's kind of tree-based. Yeah? So that's what I wanted to cover today. Now, quickly, if you go to this guy, new share. Okay? Now, this is basically what we did. Okay? And classifier, method, and all that. Try to study this. This is very good because what I did was, instead of trying automatic, I tried various methods. Nearest neighbor, naive Bayes, decision tree, random forest, gradient boosted tree, logistic regression, blah, blah, blah. But I could just use one. Okay? Just use one. Now, the difference here is that instead of giving the whole 150 data point, I give maybe like 80% of it to train, then I test on the other one, right? So the function I use is this one called take drop. So if I have, where is it? It's here somewhere. Okay. Oh, this one I don't have to say take drop because I happen to know this data has red in the first 50, blue in the second 50, and green in the third 50. But if I have a data set, okay, let's say X is equal to rand. Okay, I have a 1,000 point. I have a 1,000 point. Okay, I have a 1,000 point, right? And I want to separate into a training set. I would do this. Train test is equal to take drop X. Now, how many do I want? Let's say I want the first 700. Okay. So now my train, okay, has what length? 700. In other words, it takes the first 300 as a train. So when I train, I'm going to be something like, my classifier. Yeah. Now this is only X, right? So to make it a training pair, what do I need to do? It has to be something like X to Y, right? X to Y. So my data set, okay, is table X I to Y I okay, I to 1,000 or something like that. It's gonna look something like this. Okay, it's gonna look like that. Now, then I can do take drop. So when I say train, my classifier equal to classify this. Okay, train set method decision tree. Okay, so I get this, right? And then I want to evaluate how good it is. I would say my performance is equal to classifier measurement of test set of my model. My classifier with respect to test set. I would do this. Okay, so this is the flow of things. So I will separate my training set with a pair of X, Y, Y, Y. Okay, let's say 1,000 of them. I'll take the first 700. Now there are more sophisticated methods of selecting. I'll talk to you about that later. Info validation. But in this case, you're training with the first 70% or 80%, and you're testing the other 20 to 30%. Okay, so you build this model. This is model builder. Build model with the training set. You can specify method to decision tree or neural network or whatever, right? But when you do that, you can test performance, and that's going to get all the confusion table. And have I told you the confusion table example? No? Okay, okay. Maybe I'll make sure you don't have. Okay, performance evaluation. Now, let me show you what it looks like for this case. For this case, okay, this is my data iris. Okay, I make the data iris. Okay, Fisher iris data. It has, okay, sepal length, sepal width, petal length, petal width, and the species. Species is ABC or red, green, blue, or. Okay, it's actually, the name is versicolor or something like that. Okay, setosa, for example. Okay, so if I look at this guy, let's do this. I know that they said it in such a way that the first 50 and the second 50 and the third 50 are different ones. So okay, I do this. Right? See? So this is my sepal length, sepal width, petal length, petal width of a setosa. This is my sepal length, sepal width. Okay. Now, obviously, I can, give you this. So the way to do it is to make this an input. This is an output. This is an input. This is an output. Okay. So this is what I did here. Okay. Did here. And I make classifier. In this case, I'm doing all kind of classifier all at once. Okay. Once. Okay. But I can say something like method. I'm just going to do this. I'm going to forget about doing many classifier. I'm going to say, let's make a decision tree. Okay. Method is a decision tree. Right? Good. Okay, now pay attention. This is a, on an exam, obviously you won't have Mathematica, right? But I can certainly say, what does this function do? Okay, so what does this do? It builds a classifier based on the data set using decision tree. Now, it says the measurement is, okay, okay, my accuracy, my performance equal to this. Okay, now I can do this. confusion matrix plot. There. This is my model, right? This is the predicted plot. This is actual plot. This is actually setosa. Out of 15 setosa, remember, because I'm separating 70-30% split, instead of having 50 of each, I have just 15 of each. Okay? Out of 15 setosa, I predicted 14 of them. Right? So that's good. Okay? But what's my error? What's my error? Confusion table. What's my error? Okay? Now, obviously, you won't be running matrix, confusion matrix in an exam, but I can print a decision matrix just like this and ask you to make your statement. Okay? So, what is my true setosa prediction? So, given that it is setosa, what's my correct prediction? It is setosa, and I call it right. It is true positive, right? So it is 14, but what do I divide it by? I divide it by 15. Okay? Okay? Right? Out of this, out of 15, I identify 14 of them. This has another word, it's called recall. But if I divide this way, out of those that I say setosa, how many are actually true setosa? That's called precision. In this case, my precision is 100%. Because if I say it is setosa, it is setosa. Okay? Similarly, if I do versicolor and so forth, right? So this is what's called a confusion matrix table. Now, let me warn you that when you look at confusion matrix table, sometimes they do prediction on this axis and actual that axis. Sometimes we do it the other way around. A good example would be if you go to Wikipedia. If you go to Wikipedia page, Wikipedia confusion matrix. Okay, you would see that they put actual on this axis. Okay? So sometimes it's the other way around. Just flip horizontal vertical. But the point is, I just want you to do two things. Look at any confusion matrix and tell me what the precision and what the recall is. Yeah. Precision is out of the positive recall. I say these are positive. These are positive. They are identifying cats. These are cats. These are cats. How many really cats are cats? Given that I say cats, how many are real cats? Recall is the other way around. It says these are the cats. How many did I say are cats? So it has a different kind of interpretation. So think of something like these are your target finds. Precision would say, if you identify these finds, are they really your finds? That's your precision. But recall would say, hey, have you left anybody out? If these are your clients and you only call this many, then the other one gets left out. That's your missed opportunity, right? So recall says that you're not missing out. Okay? So this precision call, now, if you're talking about the overall accuracy, then obviously what? It is the number of diagonal cases divided by the total number of cases. Because it doesn't matter what error it is an error. That's the two positive and two negative divided by the whole thing. That's the overall accuracy. Okay, so this page actually is very, it gives you all the details. Okay. all the details. But I think it's an opposite. When you go to Python, learn Mathematica, I think the predicted and actual are plotted on the opposite axis. So be careful, okay? Don't just say it's always the top left, top right. It may be the bottom left. Get all this index. You don't need to know that. Okay? You only need to do two things: precision and recall. Recall within the context of recall confusion matrix. Yeah. You find plenty of resources in that. Okay. Actually, I'll put that in the note as well. And I'll give you the But certainly, you can see that there are two different kinds. Now, I guess we're running out of time. I might not get back to the determinant. Okay. Yeah. But definitely, think about this, by the way. Think about a judicial system, yeah, versus a marketing campaign. Okay? Think of judicial system versus marketing campaign. If I say somebody is guilty, yeah, if I say somebody is guilty, yeah, I want the people I call guilty to be real guilty, right? That's my position. So in a judicial system, position matters a lot. You're going to say these people who go to jail, they are really guilty. Yeah, the position matters a lot, right? But if it's marketing campaign, what matters? It's recall, right? Because you can always sell to people that of all the people who are potential buyers, I want to get as many of them as I can. So I don't want to leave anybody out. So I want my recall to be big. But recall and precision work off against each other. Okay. So the final things, okay, I'm forgetting about this determinant thing. We'll come back afterward. Okay, the final thing is to go to this thing called receiver operating characteristic. Okay, this one also has ROC plot. It's called ROC. Where is it? ROC curve. Sorry. Okay. Okay. Now, this is a. Oops. I have to share. This thing is my ROC curve. Okay. Let me make it a little bit big. Basically, this is giving you false positive rate versus recall. Okay. What happened is it? Okay. Let me go to this one is unrealistic because it's getting perfect prediction. Let's go. I'm going to go to the internet because it's going to give you more. In real life, you're not going to get perfect prediction. So let's go to Wikipedia or something. There. Yeah. ROC curve. Yeah, let's go to this. This is more realistic. In real life, you're not going to get perfect prediction like that. Yeah. It's a picture from the same page. Sorry. Now look. Those three lines have three different models. Okay. Every time you have one model, you get one line. On the horizontal axis, it is false positive rate. On the vertical axis, it is positive. Now, what if I want to identify guilty person, or I want to identify bad debt, or I want to identify setosa? Just one thing, it's binary, okay? If I don't identify anyone, do I get false positive? I don't select anyone. I don't select anyone. I don't get any false positive, right? Because I don't select anyone. But I also don't get any true positive either. So I get 0, 0. This is over here. All right? What if I say everybody is guilty? Everybody is setosa. That means I get perfect 100% of both, right? All the positive, true positive, I get 100% positive. But I also get 100% false positive as well. Okay? So between saying nobody's guilty and everybody's guilty, I should say somebody's guilty, but not everyone's guilty, right? Well, if my ability to judge is random, the rate of false positive and true positive goes up at the same time. So it is the diagonal, it's a 45-degree line. Okay? So if I'm over here, I'm getting 50% of all the false positive, but 50% of all the true positive as well. Right? Okay? So 50% go to jail even though they're done, and so forth. Obviously, I don't want that. I want what do I want? I want my true positive to outpace my false positive. So I want it to be this way. So the bigger the bulge, the better. The bigger the bulge, the better. Okay? That's why I said the last example in my mathematics is not realistic because it's perfect. It's 100% perfect. Okay? In real life, you won't see that. You see something like this. So if the perfect is 100%, basically this square, and this is random, so you can think of the area under this. This is called area under the outer, or AUC. And that's the performance measure of your binary discrimination model. Okay? Because again, it cannot distinguish two at a time. That's why sometimes, even though you have a multiple class, you have to break it down to a binary because you can do this kind of analysis. Okay? So, a good model will have AUC of over 70%. Okay? If you get over 80, you can buy a mobile. If you get over 90, you're really lucky. Okay? I've been in both situations. I've been in situations where in real life, 0.70 is acceptable and it's considered good enough. I've been in a situation where for some reason my client's data is so well separated, I can get 0.92, 0.93 AUC. I've been in both situations. Okay? So this is really a discriminant power. Okay? Okay? Now, notice that this is more informative than what? Than confusion matrix, because confusion matrix only gives you true positive, true negative, false positive, positive at a given point. So it's like if I'm making a point here, I can draw a confusion matrix. Okay? If I'm more stringent, I have another confusion matrix. Right? More stringent, sorry, this way. If I have more lax selection, I have confusion matrix over here. Okay? Again, what's the difference between judicial system and marketing? If it's judicial system, where do you want to be? You kind of want to be sort of like here. Okay? That means that you don't get any false positive. But you don't get false negative, false positive. What's false positive? The guy is not guilty when you send him to jail. That matters a lot. So you also don't get too positive, meaning you let a lot of people go. In a judicial system, that's considered okay. It's better to not put an innocent person in jail, given that you will let a lot of guilty people go. That's what civil liberty means. Okay. So in a judicial system, you be kind of over here. Okay, you be conservative. What if your target is my client, and your action is not sending the person to jail, but the action is to send SMS proposal? Well, then you can afford to do this, right? Because you want to get as much positive as you can. If you get all positive, then fine. That means they just get annoyed with your text. It's not so harmful, right? And in fact, that's why you get a lot of irrelevant sales hit at you. You go to YouTube and there'll be like some advertising thing that has nothing to do with you whatsoever. It's because from their perspective, you are a false positive. It's okay. You just get more. It's not so bad because it doesn't cost them anything to send SMS, right? So marketing guys are over here. The point about marketing guys is you want to get high recall. If somebody's going to buy your thing, you don't want to not send an SMS. If you send an SMS to people who are not going to buy your thing, it's okay. They'll just ignore you. They'll just say, oh, how annoying. That's why marketing is annoying. Marketing is annoying because it's targeting a lot of too positive, accepting a lot of false positive. You get annoyed because you were falsely identified. That's fine. Okay? So this is, again, all these things are statistics. Remember I told you that statistics ended up being a visualization of the result of your machine learning. Okay? That's what I said at the beginning of the class. Now, I like this picture because it's very realistic. I think it's from real data. If you have two models, one is over here and one's over there, then one clearly dominates. Let me draw a picture. This is model B, this is model A. Which one will you choose? Choose model A, right? But sometimes it goes like this. This is one model, this is another model. So this one is better over here, that one is better over there. So it's better when you're conservative, it's worse when you're liberal. This one is better when you're, this is more like a marketplace model. This is more like a judicial system model. But a lot of times it doesn't just cross one, it crosses a few times. So that's what this picture looks like. And this is extremely, I think this is a real problem. This picture that you see. I think this is a real problem. I see like this, I see something like this. Occasionally, I would see something gets dominated, perhaps, but not often. Okay? Now, once again, my experience tells me that if the A to Z is similar between a neural network and a decision tree will be more useful. It's like say, if statistical and machine learning have the same accuracy, which one would you use? Use statistical model that will give you a lot more information. Yeah. It's that kind of thing. Right. So, in the exam, what I'm going to do is I'm going to give you a 12 problem, and two would be like a bonus. It would be like a based on a little bit of coding information. Okay. Oh, this is the code. What does it do? Okay. Yeah. So you don't have to worry about syntax, because you don't have to. It's not like okay, do this, write the code. That's easy, right? Some who are more comfortable with but to read the code and say what does it do, certainly that's doable. So I'll make those two like a bonus. Sorry? Yeah, like a bonus. Yeah. The 10th problem will be anything up to date. Okay. And especially the reading the performance would go over it probably. Yeah, everything up to date. From presentation of data all the way to different machine learning paradigm, right? Also, how does this algorithm work in principle, right? How does it go downhill?
So it's all like a short answer or like short paragraph.
Yeah, you can't make that long. Yeah, so be precise. Okay. I think the easiest thing is just give you paper. So you guys have not bring anything. Okay. Don't bring laptop. Don't bring telephone. Don't bring anything. Just a pen. Right. Pen. And you write the exam in that. I'll give you plenty of room, but for precise answer. Okay. If you see like headline, you have to fill all up. Okay. Just get to the point. I prefer that. Yeah. But some people are a little bit long-winded. Takes a while to get to the point. So there's plenty of space. So it's going to be like that. It's going to be more, at least for now, conceptual. That what all this means. Okay. Even if I'll ask you about specific algorithm, just kind of describe. So I say 4i equal to 1 to n. That's not my thing. That's what you're saying. Okay. The implementation really is. But the principle is how do you know to get the best answer? How do you know where to start? Right? How does it improve? Where does that data enter? Okay? How does machine learn? Okay? And what kind of principal problem that this thing gets applied to? If you see this kind of problem, what kind of thing you look up? Why is this good at me? Why is this good at me? Okay? Why would something like this not make sense? Why would something like that make sense? Okay? And why would, for example, why would you say about data set? Okay? So all this is there. Again, within a day or two, I have something to do on Friday. But I'll try to get the most recent version of interactive notebook done by maybe Wednesday. Right, and I'll put it on a courseware or put it along with so a bit of mathematical background again is good on the linear algebra and calculus. But certainly today, something like this, the concept of why would you prefer decision tree over neural network if they have the same performance in terms of identifying blue from green or bad bet from good bet. Why? After you tell that, you have to do it. Yeah? And that's what I mean. Yeah? So you have to be able to tell yourself and then write down that explanation. Yeah, and again, two bonus will be given in terms of actual code. So, oh, what does this do? What does it not do? We don't have time to talk about the determinant and guidance system, which is extremely useful. So I'll come back after that, and I have my TA remind me that we left that part. Okay, it should have been, if you had enough time, should have been covered during the linear algebra background. Yeah, but I'll come back to that. Sorry about that. Okay, but it's extremely useful. Good. Okay, so next week is the exam, right? Just bring your pencil and your clear mind. Like that. Pen. Okay, I'll see you guys in 2 weeks.